complicated going on here, theoretically speaking, if you stop and think about it for a minute. Because what we're doing is we're forming this sequence arranged from all of the sequences that add together to give you the the original F1.
It's just another sequence, right? That limits to F, essentially.
Right, but we have a sequence of sequences, right?
Yeah.
The point is that you still have countably many things, so you can enumerate them, and that's what's happening here. We're arranging them somehow. We're not told how, but you can do it, right? And then here's the heavy lifting. Actually, is from some Calc 2 theorem, in some sense. All right, then F is represented by H1 plus H2 plus dot 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 dot. And you notice that the integral of F is in fact equal to the integral of H1 plus the integral of H2 plus dot 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 dot, which is equal to the integral of F1 plus the integral of F2 plus dot 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 dot.
Is the count proof that like if you find a sequence that converges to a similar thing, and that's like if one sequence converges, then show that it's equal to another sequence without all conversion?
It's that when we have a series, let's see here, I think it goes back to, all right, so let me just recap here. So to say that this right here, right, it presupposes that this is the case.
Yes.
Which then means that we're looking at sums of things of which the absolute value is less than infinity, which is to say that they're absolutely convergent. But for such things, you can rearrange the sum any different which way by Riemann's rearrangement lemma. Well, excuse me, the opposite of that. The absolutely convergent series can be rearranged and it doesn't alter their what they converge to. In contrast, if you have a conditionally convergent series, Riemann's rearrangement lemma says you can rearrange it to be anything you want, right? But this is not. We have absolute convergence, and what that means is you can reorder these things, right? But if so that's being used, I think, here because we also know that oh, I'm sorry, I've lost track of. I'm trying to understand how that, 2 to the minus n is being used, Audric. Do you understand it?
I'm not too caught up on that, more so than I'm caught up on like if you can have a sum less than infinity of a sequence of sequences. Because like, if you have a given function with, that is a sequence of that function, and that is finite, you would think that.
Well, but what do we mean by that's finite? Like what's finite according to that,
Well, it's less than infinity, it's like the sum of all the step functions.
That, right?
I'm going back to the original.
I know, I'm just saying like the
But yeah, I can see that like, well, technically it's a sequence of a sequence, and that is.
So I guess, to be, we'd have that the sum k equals 1 to infinity of the integral of the absolute value of f n sub k is less than infinity, right?
Yeah, essentially like I was.
For each n.
Yeah, there was some legwork there that like is obvious if you kind of think through it, but I kind of just needed to think through it.
And then, and then for each n, okay, so for each n, we also have that Yeah, let me try to write it out. All right, so there,
Thinking about it was pretty easy.
it's, yeah. Let's write it this way. The sum n equals 1 to infinity of the sum k equals 1 to infinity of the integral of the absolute value of f of n sub k, right? Like that. So that's less than or equal to the sum n equals 1 to infinity of the absolute value of the sum of k equals 1 to infinity of the, excuse me, I meant to say absolute value of the integral, I believe. Oh, no, that's fine. We should just leave it like that. What am I doing? I'm messing it up. Let me just leave it. Did you already move the camera?
Yeah.
Okay, cool. Okay. So then what? Can you see that, Audric? I don't.
Yeah. So then you just sum the integral of the absolute value of the sum of the absolute delta or something.
Right. Yeah. This here, right? This is the sum. We could rewrite this. This is the sum. This is the sum k equals 1 to infinity, right? K 1 to infinity of the integral of the absolute value of f of n sub k. And so in light of that, this is less than or equal to the integral of the absolute value of fn plus 2 to the minus n, which is, then equal to the sum n equals 1 to infinity of the integral of the absolute value of fn plus the sum n equals 1 to infinity of 2 to the minus 1 over n. And now I've made good on my claim that the geometric series is here explicitly so. So this is less than infinity by assumption, I believe. Is that right? Oh yeah. By assumption, A. So that is by, back to our definition of what this is less than infinity. This is less than infinity by the definition at the start of section 2.5. All right. And
sorry, you got the 2 to the negative. The inequality came from every single one of the k's. For each one of the sequence f. On the sum of the k is convergent to something.
oh yeah, that is from over there.
Yeah. Oh yeah. Sorry, we're back to A. Yeah.
Let me.
Oh, you're right.
No, you keep writing. You're fine.
I switched it back.
It's all good. So, like I wrote something else in there. Like the point is this is that.
Oh, itself, and you just plug it in.
And that is less than or equal to this plus that.
Okay.
But then we're summing, as Audric has pointed out, we're really, the book doesn't bother, yeah, go ahead. The book doesn't bother to actually write down what we're writing at the moment. It just kind of does it. Then the point is, this is less than infinity. Because, why? Because we wrote f is represented by f1 plus f2 plus dot, 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 right? Part of that is assuming that this is less than infinity for those integrable functions, okay? And then that is just, what is that? Well, that's, a half plus a fourth plus, that's 1/2 over.
Yeah, the geometric, you get a...
Also known as 1. So that's infinity plus 1, which of course is less than infinity, Therefore, this is less than infinity. And I think if we traced it out, it's for the same, let's see here, that's what we need if we go back to the definition of Lebesgue integrable back, in section 2.2 or 3 or wherever it was we first threw the...
Is that one used, like the original?
Yeah, the original Lebesgue integral was 2.
That's all you need is
right, that's less than infinity, and then it's going to be Lebesgue integrable on all x such that the the sum, there's the condition B requires that you need the well, just erase the integral here, right? And add an x. So
B is just that the absolute value is also, so that sum is also less than infinity.
right, and but it's just this, right?
Yeah.
Well, I should say f of x equals to that, yeah. For every x such that that's less than infinity. Well, excuse me, I'm still saying it wrong. It's equal to this for x such that what? But anyway, I think that's explicitly what we'd be wanting here in this current section 2.5, yeah? I mean, I'm just following your lead, Audric, and expanding it in gory detail.
Yeah, well, I think he skipped steps, which I understand why, but
Yeah.
yeah, it took me a second to parse through it.
And then the
Convinced that was less than infinity at first.
and then so once we have that it is in fact Lebesgue integrable, this follows because we we know that the series of the integrals of the absolute value, we know that this series is absolutely convergent, which means that you can rearrange the terms, but that's tantamount to saying that the integrals of the h's can be rewritten as the integrals of the f's, which is then to say that the integral of f is equal to the sum of the integrals of the integrable functions which are representing f. Oi, oi, oi. All right, let's go on. Let's go on. On. Ever onward. Let's see here. Where are we? I don't think we need this anymore. So corollary 2.5.4 says if you have f1, f2, in L1R, and if you have the sum n equals 1 to infinity of the I've lost my integral of the absolute value of fn is less than infinity, then there exists integrable function f such that f is represented by a sum of f1 plus f2 plus . So this corollary, I think, goes the other way, right? We were saying that if you take a, is it saying it's going the other way? I'm just going the other way. What's going on here? Oh, we started with a function which was represented in theorem 2.53. Now we're taking a series of integrable functions and saying that you can build a function from them, provided that this condition is met. And he actually gives a formula for the function, which is kind of, I like proofs that are formulas. It makes me happy. Here's his proof. Define f as follows: f of x equals to, here you go, the sum n equals 1 to infinity of fn of x, all right, whenever what? Whenever the series of the absolute values of fn of x is less than infinity. And we'll make it 0 otherwise. And if you take a step back and look at it, you'll realize, oh, okay, well, we've defined a function that is built from the series of functions. And if we apply theorem 2.53, I think then we've got what we need to see that that function so constructed is in fact, integrable. And so all right, so that brings us to section 2.6, which I'd like to start. Let's see here. Well, I probably should stop here. Section 2.6, I don't want to like half, it's going to be awkward if I just kind of go a little bit into it, but let me just tell you what's about to happen. So we're going to observe that we have a norm on L1, all right? And the norm is just going to be given by the integral of the absolute value of the function, all right? It's going to be the L1 norm, as he calls it, all right? And then after that's introduced, he's going to talk about something being a null function. A null function, let me just write that on the board. We'll try to get that in start thinking about this. And what's a null function? What's a null function? Has the integral of the absolute value of f equal to 0. This is a null function, all right? And then he gives some characterizations of how to get new null function, how relate one null function to another, all right? And then he defines convergence relative to this L1R norm, and he's got some kind of funny language for it, He talks about convergence in the norm, which means we're going to talk about a different kind of convergence as well. So we need to distinguish convergence in the norm from what we're going to call convergence almost everywhere. So he has some theorems here. And then section 2.7, convergence almost everywhere, is really what I really wanted to get to today. He starts with, definition, a set X is called a null set, or a set of measure 0, if it's the characteristic function of a null function. All right. So what's a characteristic function? What does that mean? Characteristic function of a null function.
How we define it D.
What's that?
How we define a characteristic equation.
No, it's like that thing I did at the start of all this with the chi thing.
Oh, yeah.
So, yeah, so it's an.
It's in the half open interval.
Yeah, let me write it down. A null set, let's say S, has the integral of the absolute value of the characteristic function of S equal to 0. That's a null set. A null set is one for which the integral of the characteristic function in the Lebesgue sense is 0. And then we'll find out that you'd like to say that L1, that we'd like to say that this vector space is a Banach space, but you can't quite say it because the null sets kind of mess up the story. And so it's a little bit of a technical nuancing, but eventually he gets to the point of defining, convergence almost everywhere, and then contrasting that with convergence in the norm. We'll hopefully talk about all this next class, and then finally he defines. Oh man, I've lost track of it. But he defines he goes to defining equivalence classes of functions, which basically the equivalence class is given by the set of all functions which agree almost everywhere. So like the equivalence class of f is like all g such that f of x, such that f is equal to g almost everywhere. And almost everywhere just means that they basically differ on a null set. And so that means that the integral of f and the integral of g are the same. The basic idea that we're getting to once we get there is just this thing we've observed all along, is if you throw out a finite set of points from an integral, it shouldn't change the integration. Well, this is a way of treating that carefully. That's what this is addressing. And it matters if you think about differential equations, right? If you remember Laplace transforms, we talk about the inverse Laplace transform, right? Which is a kind of funny thing if you start thinking about it, because if you think about it, if you took the function that you're finding the Laplace transform of and you changed it at a couple points here and there, it wouldn't change the Laplace transform because the integral is insensitive to like one point being removed, you know, or moved. So how is it you can talk about an inverse transform, because the forward transform is not one-to-one. All of those different slight, you know, null set modifications, if you will, of the function will give you the same Laplace transform. And yet, we talk about the inverse Laplace transform. That's because we're not working, in some sense, with functions. We're working with equivalence classes of functions, all of which integrate to the same thing. Truth be told, that's what we're doing. And you know, you can sort of smooth over this by just insisting the inverse Laplace transform be the continuous function. Or you can make some sort of ad hoc rule to select one of the equivalence class of the infinity of the equivalence class of functions to get rid of this problem, like logically. Or you could just not talk about it, and engineers will never notice in a million years. So you pick your poison. But anyway, I think that's where we stop for today. I wonder if 55 minutes. Well, that's only 5 minutes